Okay, so we watched this short little video, and I had you write down observations and ask any scientific questions.
Very dramatic version of the flame test demonstration here. First we have alcohol burning blue, then we have some barium chloride with the barium ions burning a yellow, a dirty yellow color. Then we have boron being green, strontium giving us the crimson red color. Next is calcium giving us the orange. Not showing up very well here in the next one, but the red tints inside of that orange there's some impurities there. That is lithium. Next we have sodium giving us a characteristic yellow flame. Then we have copper with its green color. And finally, potassium with the purple or lilac shade.
Okay, so I had you guys share your observations. You might have noticed that there's different colors. Different elements seem to be getting different colors. Some of the heights of our flame are different. So those are all good observations that you might notice. Also, we thought of some scientific or testable questions. So you could maybe think about some questions that were brought up today were, what if we mix some of those different compounds together? Will it change the color? What if we change he said there was alcohol being used to make it, make the flame. What if we change the amount of alcohol? Will that change the height of the flame or something like that? So these would all be testable questions. So we're going to be exploring this idea of these elements giving different colors, and we're going to explore that in the next several lessons. Okay, so these colors that are produced, we can describe these by using the word emission spectra that we learned about. Okay, so Bohr, from our Bohr model, same scientist, observed that light was given off when several elements were heated, just like those in the video. They had a different color of light when they're heated. So different elements give off different colors of light. So because of this, we can take that light and put it through a prism, and it gives us a series of different lines. It's called the atomic emission spectra. So we can call it that. It's also sometimes referred to as bright line spectra. So here's a visual. We have our gas. It goes that we heat up, and it has light. We put it through a prism, and we get different distinct lines based on the elements inside of it. Okay, so the reason this happens is because of the electrons. So we have different energy levels for our electrons. Our shells or energy levels, they have different amounts of energy. The ones closest to our nucleus have the lowest amount of energy. The ones farthest or the highest energy level have the highest amount of energy. So closest to the nucleus, low energy. Farther away, we have higher energy. Okay, so here we had a checkpoint question. So pause the video and try to answer this question on your own. Okay, so which energy level has the greatest amount of energy and is the farthest away? That would be our fourth shell in this example. We can't have more than 4 shells. In that case, it would be whatever is the biggest or largest number, but it's the one farthest away is the fourth shell. Okay, general rule of thumb, and try to answer this question. Pause the video and try to answer this one. Okay, this one is B. The farther an electron is from the nucleus, the greater its energy. So close to the nucleus, low energy, farther away, high energy. Okay, so we can describe the location of these electrons by describing it as ground state or excited state. This is depending on the positions of those electrons. So ground state electrons are occupying the lowest energy level possible. This is what we deal with that's found on the periodic table. This is what we've been dealing with so far. This is the normal way we write our electrons. So we have 2 electrons on the first energy level, 8 electrons on the next energy level, and so forth. But we can also have electrons occupying what's called excited state. So here the electrons are occupying a higher energy level than they normally would. So here we have a picture, you know it's exciting, electrons moving to higher subshells. So they become excited if they move up. Okay, so as we're going from ground state, that lower shell, to a higher energy level, we are absorbing energy because it needs that energy to jump up to the next level. That's what's shown here. But then as we go back down, excited to ground state, we're releasing energy, and as it does that, light is released and emitted, and this is what's going to create that bright line spectra that's unique to each individual atom. And if you can think about it, it's going to be different for each atom because the electrons are different in each atom. Okay, so here's another checkpoint question. What's the difference between ground and excited states of the electron? Okay, this one would be A, excited states are when electrons move to a higher energy level upon gaining energy. That higher energy level is our excited state. They're at ground before that, and then they gain energy and are at excited. Okay, so our ground state, this is showing a chart with aluminum and boron, Al and B, as examples. Our ground state, this is how our electrons normally are. So for aluminum, we can look on our periodic table and see how many electrons aluminum has. And so we know that the first 2 electrons will go on the first energy level, then 8, and then it will fill up the third. So we can write the electrons as 2, 8, 3 for aluminum because aluminum is number 13 on our periodic table. So we can know 2 electrons are going to go in the first energy level, then 8, then 3. This is not any new information. We just call it ground state because everything is occupying the lowest energy level possible. So then we can have excited state. This is when we have added energy and some of those electrons have bumped up. So examples of these would be like 2, 7, 4, where an electron from that second energy level has jumped up to the third energy level. Or 2, 8, 2, 1, where an electron from that third energy level has bumped up to a fourth energy level. I would not require you guys to write examples of the excited states, but you should be able to look at one and recognize that it's excited as opposed to a ground state. So ground state, everything is occupying lowest energy level, how we would normally write it. Excited, something's bumped up. Okay. Oops, I meant to have you guys try that one on your own. So our boron example would be 2, 3, because it has 5 electrons total. So 2 electrons on the first energy level, then 3 on the next. So an example of the excited state could be 1, 4, where we've bumped up an electron from the first energy level, or 2, 2, 1, where we've bumped up an electron, from the second energy level. Okay, so we're going to answer this question, which the second principal energy level can hold up to how many electrons in it? So pause the video and try it. Okay, this one's going to be 8. It's going to hold up to 8 electrons. Okay, so why is the electron configuration 2972 wrong for potassium's excited state? So try this one. Okay, this one is A. You cannot have more than 8 electrons in the second energy level. So you may have noticed before with when we're going to an excited state, we bump up electrons, but we can't bump them up to an energy level that's already full. So there wouldn't be an electron here. Also, it would have to come from the lower energy level, which already has 2. So it can't, I don't know where that extra electron came from. Okay, so looking at the periodic table, what would the electron configuration for aluminum in its ground state be? So try this one. Okay, this one is 2, 8, 3. I probably shouldn't use aluminum again. But anyway, we can look easily at the other ones to tell why they are excited states, right? Because we should have 8 electrons in our second energy level. So we can see that A, we've bumped up some electrons to the next energy level. Number 2, we should have 2, 8, and then we shouldn't, the second energy level isn't full. So we shouldn't have any on the fourth yet. Same for C. So D, they're all in the lowest possible energy level. That's ground state. Okay, and so what does bright line spectra show? Try this question. Okay, so the big thing here is looking at the difference between emitted and absorbed. So our bright line spectra, that light is being produced when energy is being emitted. Absorbed is when we're jumping up to the energy level. Emitted is when it's releasing that energy. So we can go ahead and eliminate B and D. So we're going to emit light, and that happens when it falls back down, okay? Because we need to use that energy to get up to the next energy level. When it's falling down, it can use that energy to make some light. Okay, when an electron goes down into ground state from an excited state, what happens? Try this one. Okay, this one emits light. When it goes from excited to ground, it's going to emit light. Okay, so here again, we're talking about our bright line spectra, also called the atomic emission spectra. The wavelengths of light emitted are unique to each element. So we can then use this spectra to identify elements because they all are going to have different colors that are produced and different lines in the spectra when we look at the spectral lines. Okay, so this is actually kind of a fun fact. This is actually what's used to determine what different stars are made of, because we can take the light that's produced from the stars and we can put it through a prism and see the different lines that are produced to determine what elements are there. Okay, so we can use these spectral lines in order to determine what element it is. So here is an example of helium, hydrogen, sodium, and lithium's spectral lines. So we want to match these to the spectra A. And it's actually got a mixture. So we can look up here and try to find ones that match similar. And you might notice that this line here from hydrogen is similar, but hydrogen will also have two lines up here, which our sample does not. So we can eliminate hydrogen. We can also eliminate helium because it doesn't have these lines at the front. So this one is a mixture of sodium and lithium. We can see that these two lines correspond to those two, and these two lines here correspond to those two. So try this next one on your own. What are they comprised of? Okay, so this one is going to be hydrogen and lithium. You can see that this double line here for sodium is not present. So it's not going to be sodium, lithium. These two lines are present. And then these lines for hydrogen are also all present, but the line here for helium is not. So you can kind of eliminate ones based on where the lines are or are not present. Okay, so try this one to figure out what the unknown mixture is made of. Okay, so this one is made of gas A and gas D. You can see gas A is where we get this line as well as those double lines and this single line, and then we get gas D here. Notice that C is very similar, but they're slightly shifted, so it's not going to be C. We're going to have them in the exact same location. So these lines correspond to like that rainbow spectrum, and where we have the different lines, we would actually see different colors based on their locations because these are showing different wavelengths of light, but a lot of times we just represent it by lines like